Hey guys, sorry I haven't recorded in a while, but we are back today, and this is going to start my series on AP Calculus BC, and I am going to cover all topics in AP Calc BC that are not covered in AP Calculus AB. And the first topic is integrating using integration by parts. This is one of my favorite techniques, and for people who like integrating, this is very fun. So before I go into the integration by parts formula, let's try and prove it. So we know the product rule. And the product rule states that the derivative of f of x times g of x, so those are just two random functions I've denoted, is equal to the derivative of the first times the second plus the first times the derivative of the second. Now what I'm going to do is I'm going to integrate both sides with respect to x. So now I get the integral of d dx of f of x of g of x dx equals the integral of f prime of x times g of x plus f of x times g prime of x dx. Okay. And by the fundamental theorem of calculus, it states that the integral of a derivative is simply the function. So now I get f of x times g of x is going to be equal to the integral of, and now I'm going to separate these to become f prime of x g of x dx plus the integral of f of x g prime of x d of x. All right. And this is where you can see this starting to form. So I am going to rearrange the terms, and I am going to isolate this integral right here. And I'm going to move this integral to the left. And when I do that, I get the integral of f of x g prime of x dx equals f of x g of x minus the integral of f prime of x g of x dx. Now notice how cool this is. I am going to let u equal f of x, and I'm going to let v equal g of x. So du dx is equal to f prime of x, and dv dx is equal to g prime of x. So this becomes the integral of u. Now think about what g prime of x dx is. Well, that's simply going to be dv, because from this dv equals g prime of x dx. So now I get u dv equals, and now this is going to be uv minus the integral of, now f prime of x. We can see that f prime of x from this, that is going to simply just be, let's see, so we have, right, okay, so this is going to be my g of x, that's going to be v, and then I get a du, because when I solve for this, I get du equals f prime of x dx, which is what I have all the way up here, and therefore du goes at the end here, and this is the formula for integration by parts. Pretty cool. Now obviously for the AP Calculus BC exam you do not need to prove this, but it's very helpful. Now in AP Calculus BC you will have to evaluate indefinite integrals by integration by parts and definite integrals by integration by parts. And I think we should start with some examples. And there's a technique to identify which function you want to use as your u and which function you want to use as your dv. And it's called LIATE. Now, some people use LIATE, but I use ILATE. This stands for inverse trigonometric, logarithmic, algebraic, trigonometric, and exponential. Now, basically what this is saying is inverse trigonometric functions take priority over everything in determining u. Now, this is only a tool. This is not a definite list. So 99% of the time you will use this ILATE rule, but sometimes it could be different. So let's go into some examples. So the first example is the integral of xe to the 5x dx. If we try to use normal integration techniques here, it's not going to work. But I can use integration by parts. I'm going to let my u be x, and I like making this box. So we have a box here. And then you can simply say, here's u, here's du, here's dv, and here's v. Because algebraic takes greater precedence than exponential, x is going to be here. The derivative of x is 1. E to the 5x is here. The integral of e to the 5x is 1/5 e to the 5x. So now I get that the integral of e to the 5x dx is equal to x over 5e to the 5x uv minus the integral of, I can take out a 1/5, e to the 5x dx, and this equals x over 5 e to the 5x minus 1/25 e to the 5x, and do not forget to add your constant of integration. So that's our first basic example there. And then we can do a couple others. So what if we have the integral of 4x cosine x dx? So this integral right here is a little bit different because now we have a trigonometric function, but that should not scare us. We know that from ILATE, algebraic still does take precedence. So most likely, I'm going to put 4x here, and I get 4. Cos x here. Now the integral of cos x, remember, is sine x. So now I get the integral of 4x cosine x dx is equal to 4x sine x minus the integral, and I can take out a 4 sine x dx, and this is equal to 4x sine x. Now the integral of sine x is negative cosine of x, and I have a negative, so this turns into plus 4 cosine x plus c. So that would be the answer for that integral. Now here's a trickier one. What if I have the integral of ln x dx? Well, I only see one function here. How could I think of two functions? And you have to think about this outside of the box. So I have that ln, but notice this. Look at how I can rewrite this integral. What if I just express it as the integral of 1 times ln x times dx? Well, now it looks like I have a function. It's 1. But if I just take the derivative of 1, I get 0, and that's not going to help. So what if I try putting 1 here? And I put ln x here. Well, the derivative of ln x is 1 over x. The integral of 1 is x. So now I get the integral of ln x dx is equal to x ln x minus the integral. Now 1 over x times x is 1, so I just get the integral of dx. And therefore this is equal to x ln x minus x, and do not forget that constant of integration. Now one more harder question is the integral of x squared e to the 2x dx. How do we approach this one? Well, this is what I call repeated integration by parts. I'm of course going to start. X squared is here. It's algebraic. It takes precedence. Here's my exponential. Derivative of x squared is 2x. Integral of e to 2x, 1/2 e to 2x. So the integral of x squared e to the 2x dx is equal to 1/2 x squared e to the 2x minus the integral. Now notice 2 times 1/2 is 1. So x e to the 2x dx. So now I can do another integration by parts on x e to the 2x. Here's x, here's e to the 2x. This becomes 1/2 e to the 2x. This becomes 1. So now I get the integral of x squared e to the 2x dx equals 1/2 x squared e to the 2x minus 1/2 x e to the 2x minus 1/2 integral e to the 2x dx. And this will equal 1/2 x squared e to the 2x minus 1/2 x e to the 2x. Now the integral of e to the 2x is 1/2 e to the 2x, so that's negative 1/4, but this negative here distributes, so that's really plus 1/4 e to the 2x, and do not forget that constant of integration. So you can see that repeated integration by parts does get quite annoying. Now, let's say that you want to do a definite integral for one of these. Well, it's quite simple. So let's say we have the most known example is x e to the x dx. And say I want to take that from 0 to 1. All right? Well, how do I do that? Well, it's just the same thing. Put your box. I know my x is going to be my u. Here's e to the x. That's 1. That's e to the x. So I get the integral from 0 to 1 of x e to the x dx is equal to x e to the x. And you evaluate this from 0 to 1. And then you do minus the integral from 0 to 1 of e to the x dx. So you're just basically separating it. The uv gets the bounds, and the integral gets the bounds. So now when I evaluate this is going to be e minus e minus 0, so that's just e. And then the integral from 0 to 1 of e to the x dx, well, that's going to just be e to the x from 0 to 1, which is equal to e minus 1, right? Now, notice that I'm also subtracting. I have this subtraction here. Don't forget about that. So now I have e minus 1. Look at how cool of an answer this is. My e's cancel, and I simply get 1. So this is the lesson on integration by parts. And the next topic that we will cover is integration using linear partial fractions. Stay tuned.